So the program, the next talk would be by Mikhail Zamkovsky. So it's just on search on heavy neutral leptons at Na62 at CERN.
Yes, exactly. This will be experimental talk. I'm not a theorist. So I will briefly sum the results of Na62 experiment at CERN and also tell you about some further development in this search which is going on at the experiment. So first I will try to introduce the theoretical motivation for the heavy neutral leptons, then a brief history of chaos at CERN and what kind of research was done in this direction. Then I will describe the Na62 experiment, the experimental setup, and then describe the strategy of the analysis and tell you the results from different periods of the running, from 2007 data, 2015 data, and then tell you about the further prospects based on the data sets taken 2016, 17, and this year. And then I will explore the possibility to go with the Na62 experimental setup into the so-called dump mode type of experiment, which is sensitive to different masses of the heavy neutral leptons, and I will show you the limits, what can be achieved during the data taking in this dump mode type of the experiment. So from the neutrino oscillations, we know that the neutrinos should have the masses, which is not the case in the minimum standard model. So the possible extension to how to give the masses to neutrinos is to extend the standard model by this so-called neutrino minimal standard model proposed by Asaka and Shaposhnikov in 2005. In this model, the minimum what you can do is to add 3 right-handed neutrinos with masses about, the lightest one is about 10 kevs, and another 2 more massive ones are about 1 GeV. And this first one can be used as a warm dark matter candidate, while the 2 next one can, through the CP violation phases, which this model introduced 6 CP violation phases, can account for the baryon asymmetry, and through the seesaw mechanism produce the standard model masses for the active neutrinos. So this is the picture of the standard model as it was presented already on Monday at the beginning. So this minimum neutrino minimum standard model can explain the neutrino oscillations, which is in this model fully in agreement with the data on the neutrino oscillation, provides the cosmic dark matter candidate, and can also explain the baryon asymmetry of the universe. Here are some weak interactions of the heavy neutral leptons with the standard model particles, which are interesting for us because these are the ways how we produce it or how we can study them. So the production of the heavy neutral leptons is coming from the decays of the particles like B, D, and Ks. So basically depends on the on this particle, you can get S massive heavy neutral lepton. And then as the couplings to the standard model are very suppressed, the production rates are quite small. And on the other hand, the heavy neutral leptons are long-lived particles. So in a case where you are measuring basically the heavy neutral leptons from the kaon decays, you can only see the production of the heavy neutral leptons, while, for example, in the dump mode, what you can see is also the decay of the heavy neutral lepton to something else. Because the heavy neutral leptons with about 1 GeV invariant mass has a life distance more than 10 kilometers. So the low mass heavy neutral leptons will be not seen, but the ones which are produced in the decays of the charm or B quarks can be accessible in the experiment of Na62. So these are some constraints from the different cosmological observations. So basically, the accessible mode in the kaon decays is in this region here, up to basically the kaon mass with some limit from the resolution and the statistics. And then for the dump mode, when you have also the B's and the D's, you can go somewhere in this region when the invariant mass of the heavy neutral leptons is about 1 GeV, 2 GeV, or something like that. Okay, so the production for the heavy neutral leptons, if their mass is below the mass of the kaon, is given by this formula basically, where this rho is the phase space parameter plotted here. Here is the one for the muon mode, when you have the heavy neutral lepton, the kaon decaying to muon and heavy neutral lepton, and this one is for the kaon going to electron and heavy neutral lepton. This is suppressed by 10 to minus 5, 2.5 times 10 to 5, which comes from the RK measurement, lepton universality measurement in the kaons. So this is how you can produce it in the decays of the kaons. Then on the other side, as I already mentioned, is the possibility to study the decays of the heavy neutral leptons. So if you produce the heavy neutral leptons somewhere upstream in the target from, for example, decays of the B's or charm quarks, you can observe the decay of them downstream in the active region of the experiment. And it depends on the mass of the heavy neutral leptons. So basically, the lightest one, which are from the kaon decays, will be not seen. But for the ones which are about 1 to GeV, it's already possible to see them in the active volume of the experiment. So this is possibility how to study them. So basically, what is planned to do is to observe them in this type of the decays when they go to two charged particles. So you have two charged particles in the final state, and then you have quite good signature in the detector. So this is just again saying the same, that for the kaons it's difficult, but we can see the production, while for the more heavy ones we can see the really decays in the dump mode type of the mode of the experiment. So this is the history and the present status of the kaons at CERN. So basically, the kaons have quite a long history at CERN. Started in the 80s by NA31 experiment, then continuing as NA48 experiment, which was measuring the CP violation and K zeros, and also doing some in later phase some studies with the charged beams, which was actually used to study heavy neutral leptons. Then there was the 2007 and 8 data taking during the so-called RK phase, mostly devoted to study the lepton universality, but also there was a possibility to study the heavy neutral leptons. I will mention some results from that one. And then the new NA62 experiment with the new experimental setup started. 2014 was a pilot run, and 2015 was the commissioning run, and the results I will present here are coming from this period of 2015. And then 2016, 17, and this year is the data taking mode for the main decay of NA62, which is a pi nu decay. And then after there will be the shutdown of the LHC, so the SPS will stop as well. But afterwards, 2021, the experiment will restart again, and there will be another 3 years of the data taking. And during this period, there is a possibility to have the dump mode experiment for about 1 year. Or this is still under discussion, but definitely there will be something. So this is another source of the data for heavy neutral lepton studies. So this is the what has been done during this phase here by NA48/2 experiment, where they were basically searching for the heavy neutral lepton decays, or also the this type of the same lepton number violation modes with the Majorana neutrino exchange here. So this is in the decay, k goes to k plus to pi minus mu plus mu plus. So you have the lepton number violation by 2, which can be explained by the exchange of this Majorana neutrino here. And from here, there is the limit set by the experiment. The other type of the research which was done was with the same sign muon charges, where you have which can be explained by this type of the decay, when you have the kaon going to muon and the heavy neutral lepton, which is subsequently decaying to pion and muon. And also you can extend this simple new MSM with the inflaton, with a new scalar field, and this will demonstrate itself in this type of the decay when it goes to pion and the dimuon system is peaking at some specific invariant mass, which is the inflaton mass. So there are again the limits set by the NA48/2 experiment. And then for the NA62 experiment in both phases, 2007 and 2015, there was the search in this mode where the kaon is decaying to lepton and heavy neutral lepton, and this is done again as a search for the peaks in the missing mass of the k minus kaon minus muon for momentum. And these searches are model independent. It can be whatever, not only heavy neutral lepton. Okay, so this is the experimental setup from 2007, where it's similar, but today NA62 has basically all the detectors are new. So here is the beam pipe. Here is somewhere the target, where you have this kind of beam with a central momentum 74 GeV. And then it goes into this decay tube or fiducial volume, where you have 4 stations which are used as a spectrometer. So it's a tracker with the magnet in the middle. There were 2 photon anti-counters to suppress the background, and then it goes to the set of detector with the charge hodoscope, liquid krypton calorimeter as the electromagnetic calorimeter, set of the hadronic calorimeters, and the muon VTOS. So these are some specifications of the separate components. And this is the search during 2007 data. So the search was done in the k plus going to muon and something. Well, the reconstruction is done by reconstructing one positive track. Then you require the energy in the calorimeter, electromagnetic calorimeter, smaller than 2 GeV. And then you do some cut in this space to get rid of the background coming from the muon halo, and you search for the peaks in the missing mass distribution pk minus pi mu. The signal region is in this interval, 300 to 375 MeV. So this is where the experiment was sensitive during this period of data taking. The acceptances and the resolution of the missing mass are taken from the Monte Carlo simulations with 1 MeV interval. So these are the distributions of the acceptances and of the invariant mass resolution. In total, 60 million kaon decays were found in the fiducial volume and were analyzed. And this is the picture of the data, what was measured. So here is the control region, here is the signal region, and you have a different contributions from the background and the data points as the black dots. Okay, so these are some results. So the study was done by scanning the invariant mass bins, which of size 1 MeV with the mass window size given by the resolution, so it's dependent on the resolution, and it's getting smaller and smaller for the higher masses because the resolution is improving with higher masses. And the Rolke-Lopez method was used to get the upper limit on the number of signal events, and this is the distribution of the background events. So the most or the dominant background is coming from the muon halo. It's about 5 to 20%. It's driven on the it's data-driven study, and then there are some decays of the kaons which are sneaking into the signal region, and these are done on the understanding of them is performed by the Monte Carlo simulations. But then the estimation of the background is used as a fit to the data. So these are the upper limits of the signal on the number of signal events, and this is the result for the branching ratio and the mixing parameter. So you can see that there is okay, the dashed line is the expected what we expect. Then the green one is 1 sigma, and the yellow line is 3 sigma bound, and you see that there is no event observed with the significance higher than 3 sigma. So these are the results for the 2007 data. Now we rebuilt the experiment basically from the scratch. We left only the one of the hadron calorimeter and electromagnetic calorimeter. Otherwise, basically everything has changed, and we have completely new setup. So today, and also true for the next run after the long shutdown of LHC, we will use this experimental setup. So we have a beam coming from this side, from the SPS. So it's a 400 GeV high intensity beam from SPS impinging into the beryllium target. In the beryllium target, you produce different types of the particles. 6% of them are the kaons with a central momentum 75 GeV. This is our secondary beam. And then you go into the K-tag. K-tag is tagging the photons. It's a CDAR detector, ring imaging Cherenkov detector, which is tagging the kaons. Then the particles go into the beam tracker when you measure the momenta and the direction or free momenta of the kaons. Then it enters the evacuated tank with the vacuum at the level 10 to minus 5 millibar. So it's a high vacuum tank, which is about 50 meters long or 60 meters long, the active fiducial volume. And here, these blue lines here are the counters for the photons. So these are vetoing the photons. Then again, we have the spectrometer, magnetic spectrometer, to measure the momenta of the decayed particles. So the kaons are decaying in this volume here, and then what is going further are the decay products coming from them. And as I told you, everything here is in the high vacuum. So the undecayed beam particles are actually closed in the beam pipe, so they are not interacting with our detectors. And then the particles go into the rich ring imaging Cherenkov detector, where we do the particle identification, then electromagnetic calorimeter, 2 hadron calorimeters, and the muon veto detector or muon detector. So this is the experimental setup. The main program of of Na62 experiment is to measure the branching ratio for the kaon going to pion, neutrino, antineutrino. So it's not perfectly, it's not the perfect thing to study what we want, but it's possible to do it through some other trigger streams. So the main program is this one, to measure it with the precision of less than 10%. and to measure more precisely the VTD coefficient of the CKM matrix. But again, this is like the main thing, but with some other trigger streams, you can study also these types of the decays, lepton flavor violation, lepton number violation, which is again connected with the, for example, Majorana neutrinos. Then you have the heavy neutrino searches, pi zero decays. You can also try to find some dark photons or something like this. So this is the other program. So now the heavy neutral leptons in this experimental setup was following. There were 5 days of the data taking during 2015 at 1% nominal intensity of the beam. And during this period, we got about 3 million kaon decays for the mode K goes to E plus and heavy neutral leptons, or E plus something, and 1 million going to muon and something. This is due to the trigger conditions, the minimum bias trigger, which is basically one charge drag in the final state. It's fine for both of them, but then there was another trigger which was with the muon counter in a veto, so it was vetoing these types of the events, and this one not. So there are more of these ones, and this is these are the heavy neutral lepton masses, or the resolution of the mass invariant masses, and these are the acceptances for the K mu and Ke events. So this is the distribution of the invariant mass of the data, and on the background are the simulations of different types of the events. So this is the K2, and then you have the main background contribution for these ones are from the kaon goes to muon, and muon subsequently decays to electron. So this is the main peak here. And for this is for the electron mode, and this is for the muon mode, where you see that there is some discrepancy between the data and the Monte Carlo background. So this is due to the bad simulation of the muon halo. So the muon halo are basically the muons originating from the decays of the particles between the fiducial volume and the target, so coming from the kaons, from the pions, and they are entering the fiducial volume, and they are deflected by the magnets of the spectrometer of the beam, so they can enter in the angles to our fiducial volume, so they are misinterpreted at the end. Okay, so then there is this there is the identification of the electrons and muons and so on. So these are the working plots for doing the upper limit surge or limits. Again, the mass step for the scanning of the invariant masses of the heavy neutral leptons is 1 MeV with the signal width, or the window width of 1.5 times the resolution window of this, and the background is estimated as a polynomial fit of third or fourth order from the data, and then we do the single event sensitivity studies, which are shown here. So these are the results. There is no signal for the heavy neutral lepton with the significance bigger than 3 sigma, and this is the picture for the of the results with respect to the other experiments which were done in the past, or even in the past basically. So you can see that this is the electron mode where we improved the limit above 300, or for the electron mode we actually improved the limit from 170 up to 450 MeV, and for the muons we improved above 300 MeV the limit here in this region. So again, this is based on 5 days of data taking at 1% nominal intensity. So the major improvement is foreseen from 2016, 17, and 18 data, which is now under study and under analysis. Okay, so just a brief mention of the damp mode of the experiment. So this is in the normal standard data taking condition, where you have a target here creating kaons, pions, protons, whatever in the target, and then you have the particles, the kaons decaying, producing possible heavy neutral leptons here. While in the damp mode, which is quite easy to get to, you just remove the target and put the tags instead, because it's a higher Z, so a higher production of the charms and beauties. So then you create the heavy neutral leptons at the target. They are going straight, and afterwards they will decay in the decay volume, and going to the pion and muon, you have the signals in the detectors. This is just some background for these types of the studies. So the main backgrounds are the muons and the neutrinos coming from here, because they are not stopped by the dump itself. And this is the projected sensitivity with the Na62 experiment possible during this data taking in 2021 to 2024. And you can see that we can improve up to some 2.5 GeV coming basically from the beauty bottom quark decays. And this is based on the full detection of two-track final states and the zero background. The zero background was proven to be true up to 10 to 15 protons on target during the last year of the data taking. So this is basically what we can do. And these are the results. So we improved with 2007 data the limit of the KEK above 320 MeV for the muon mode. With 2015 run, we improved the limits on the mixing of these heavy neutral leptons in region 174 for 448 MeVs for the electrons, and 300 to 373 MeV for the muons. We foreseen a major improvement when the data of this year's will be analyzed, and then there is a possibility to run also in the dump mode, and during after LS2 we tend to have about 80 days at the nominal intensity running in this dump mode version. Okay, that's all. Thank you.
So, time for questions or comments.
I'd like to comment that within a network which was led at the time, was maybe 10 years or more ago, by Freddy Egerlin, we had a meeting in Padova, and I reported there the estimate of the third root of the product of the heavy ones. That's the only one which has a real mass relation. Mm-hmm. And found that it is within errors in the exponent of factor, let's say 100 to be, it's 10 to the 10 GeV.
Right.
This was published in the proceedings of this lecture.
Okay, other comments or questions? If not, then we thank all speakers of the session again.